So far we've been doing series bandpass filter or series resonant circuits, and now we're gonna look at the parallel bandpass filter or parallel resonant circuits. So it's a circuit. So instead of circuits, I'm gonna call it a circuit. And remember, it's a bandpass filter, so objective is the same, that it is going to let a band of frequencies pass through it and stop the low frequencies and high frequencies, and only band of frequencies are going to pass through this circuit. All right, so circuit looks like this. Remember, we did the transient analysis of bandpass filters, so it's the same circuit, except instead of DC source, we are using an AC source, and we are changing the frequency of that AC source. And this is the current source. To understand the circuit better, we apply source transformation, and then instead of current source, we put a voltage source in series with the resistance, and the RL and L and C, we leave them as parallel. So we perform source transformation. And the output voltage is measured here across each component, L and C. We convert everything in the complex frequency domain, in the phasor domain. And the output voltage is going to be so that's the parallel RC resonant circuit. I should not call it RLC. It's a parallel LC resonant circuit, bandpass filter. So your C and L, they are parallel to each other. Yeah. It doesn't matter. You can connect. It's not going to make any difference if you connect in the circuit, whether it's connected between the same nodes. You can connect any element, right? You can connect any element between the same node. They will still appear to be parallel to each other, whether you connect capacitor first or inductor first or whatever. Okay. So we're going to go ahead and find h of j omega. But before we find let's go ahead and find h of j omega first, and then we discuss the resonance and all those things. So first we find the transfer function. Transfer function. All right, so who is going to tell me first what will be the output voltage in terms of the input voltage? What will be the expression for the output voltage in terms of input voltage? Okay. The voltage division between R and the parallel combination of XL and XC. So XL parallel to XC over R plus XL parallel to XC times V in j omega, right? Everyone understand this voltage division, right? Let's go ahead and find the transfer function now, which is the ratio between the output and the input. H of j omega, magnitude we'll find later. H of j omega is the output over input, which will be simply the parallel combination of XL and XC over R plus XL parallel to X. And now let's go ahead and put H of j omega. All right, XL parallel to XC, parallel combination will be 1 over j omega L. XL is, of course, j omega L. So 1 divided by 1 over XL plus 1 over XC. And XC is what? 1 divided by j omega C. Yeah. V, there's no V. Where do you see V? Oh, that, okay, that V. Yeah, the input voltage. V in, yeah, input voltage. V input. It's right here. So that's your XL parallel to XC. Perhaps it might be better we solve it first because we are using it here and using it here. So let's go ahead and solve this first and then use that equation here and here. That might be easier for us. So let's go ahead and solve that expression first. XL parallel to XC is 1 divided by 1 over XL plus 1 over XC, which will be 1 divided by 1 over j omega L plus 1 divided by 1 over j omega C. So XL parallel to XC will be equal to 1 divided by 1 over j omega L, and then 1 divided by 1 over j omega C will simply become j omega C. And let's simplify it. J omega L times j omega C is negative omega square LC. So 1 divided by 1 minus omega square LC divided by j omega L. So our final expression for XL parallel to XC is simply j omega L divided by 1 minus omega square times LC. So now we can use this instead of all right. Any question? Makes sense or no? Anything that is not clear? Ask if something is not clear. Read it and then ask. Make sense? Okay. All right, good. Let's move on. So now we're going to take this thing and then we're going to put in the equation for h of j omega because we have it in the numerator and as well as in the denominator, XL parallel to X. So this implies h of j omega is equal to j omega L over 1 minus omega square LC divided by R plus j omega L over 1 minus omega square LC. Let's simplify this. H of j omega is equal to j omega L, and then 1 minus omega square LC. I'm going to multiply this by R first, R 1 minus omega square LC plus j omega L, and then of course 1 minus omega square LC will be cancelled out by 1 minus omega square LC. So this is your expression for the transfer function of this specific filter. Now again, looking at the transfer function expression, you may not be able to identify what type of filter is that. It could be a band pass filter, it can be a band stop filter. May not be high pass, low pass because it has both L and C, but it could be again band stop or band pass. So just by looking at it, you may not be able to identify it until you plot the magnitude response of that. And once you have the magnitude response, then you can clearly see if it's a band pass filter or it's a band stop filter or a high pass, low pass, higher order filter, whatever, right? So magnitude response is very important for you to plot. Yes.
As a separate type of way of thinking, we wouldn't be able to determine that by the roots of the characteristic.
We don't have characteristic equations.
No, I was just asking. Series,
yeah,
we have that, but I was curious if we could determine.
In the series, we did not discuss characteristic equation in the filter. Even if you go back and check the lecture, we did not discuss the characteristic equation. That was the transient analysis when we were discussing characteristics equation for RLC circuits, right? I mean, you can get some idea by looking at the circuit. You can get some idea as, again, when the frequency is low, that means XC is going to be 1 over omega C, which is going to be very high. It's going to be open circuit. And XL is going to be omega L, which is going to be 0. So at low frequencies, output is going to be 0 because your L is shorted out. Likewise, so you have low value or 0 value, let's say, at DC. As you start increasing the frequency, XC value is going to start decreasing. 1 over omega C, omega is increasing, XC is decreasing, and XL value is going to start increasing. Now, two values parallel to each other, one is the small, one is large, parallel combination is going to give you smaller than the smallest value, right? So again, your output will not be 0, it will start increasing. And now again, look at a very high frequency. When, let's say, omega gets to almost infinity, 1 over omega C, XC is going to be almost 0. And XL is going to be omega L, which will be almost infinity. So again, one is 0, one is very large. You combine them in parallel. That means your parallel impedance is going to be very small because one is open circuit and one is 0. So when you go to very high frequency, again, your output is going to become 0 because of short circuit produced by X of C. So at low frequencies, it's short circuit because of omega L. At high frequencies, it's short circuit because of omega C. That means you don't have output at low, you don't have output at high. In between, you have output, right? So that's a band pass filter characteristics. Now for band stop filter characteristics, it's going to be opposite. At low side, you will have output. At high side, you have output. And in the middle, you will not have any output, basically. At band of frequencies, that is stopping all the frequencies. So band stop is opposite of band pass. Yes, Doris? So high pass filter, when you put omega and you analyze at different frequencies, you will see that at low frequencies, the output is 0. And then as you start increasing the frequency, the output start increasing as frequency hit infinity, the output basically is going to become, the output nodes is going to become open circuit. So all the input is just going to be transferred to the output for the high pass filter. For the low pass is opposite. So again, from the filter, you can establish that, but if you have the transfer function, and you don't have the filter, you don't have the circuit of the filter, but you just have the transfer function, then again, you can play with the frequency and say, okay, if it is 0, then I can see the numerator is 0. That's why my output is going to be 0. And when infinite is going to become infinity, then I have infinity over infinity. I can apply L'Hopital's rule, and then, but easy way is to plot the magnitude response, and then that will show you what is going to be, how how it is going to look like. So magnitude response, what will be the equation for the magnitude response if I want to write down the expression? Of course, in MATLAB, you don't have to write down the expression of magnitude response. You can just use the absolute value, absolute function. But if you're writing the magnitude response equation, then who is going to tell me except Yunus, because Yunus knows how to. Who is going to tell me how to write the magnitude response equation for this filter? From, of course, we have the transfer function, so how to calculate the magnitude response of the transfer function? Excellent. Yeah, I know you know that. That's very good. Excellent. So it's going to be magnitude of the numerator, which is omega L. Remember, J is the phase, which is 90 degrees. So omega L is the magnitude. And magnitude of the denominator, which is square root of the first term, real term, plus square of the second term. And that's going to be the magnitude. Excellent. So omega L over R square 1 minus omega square LC square plus omega. So that's the magnitude response expression. And once again, guys, if you're plotting this in MATLAB, you don't really have to write this equation. All you have to do, as we did on Monday and last week, you just need this equation and then use the functions absolute and angle to calculate the magnitude response and the phase response. But you need to know how to write the magnitude response equation and phase response equation, of course. Now, phase response equation. Who is going to help me out writing the phase response equation for this? Yes, Chris. The phase of numerator is not 0. 90, yeah. It did. No, that's good. Say it. No, there's no J when you're writing magnitude or phase response. Don't put J. Yeah, tangent inverse of y over x. Remember that. A plus JB, right? What is the phase response of A plus JB? Tangent inverse of B over A. So this is B, this is A. And in the numerator, of course, you have 90 degrees, J omega L. So phase response. Guys, complex number manipulation is easy. You just have to learn it once, and then it becomes so easy. But the problem is you guys don't want to learn once. That's the issue. If you learn it once, it's going to become easy. 90 degrees is the numerator, and the denominator is simply tangent inverse or arctan of B, which is omega L, over A, which is R1 minus omega square LC. And that's the phase. And remember, if you're using this equation, then make sure you have to be careful about this term if you're using tangent inverse, because if the phase is coming out to be in the third quadrant or the second quadrant, then you have to, in the second quadrant, you have to add 180. And in the third quadrant, you have to subtract 180 if you're using tangent inverse function in MATLAB or in your calculator. If you're using just angle function, then angle is just going to give you the correct angle. Yes, Rice. Which omega L? But that's B, A plus JB. So A is R1 minus omega square LC plus JB, right? Yeah. A is the real part. So this is A, and B is the imaginary part. So this is B. So tangent inverse of B over A. And same goes for the numerator. So phase of the numerator minus phase of the denominator. And remember, in numerator, your A is 0. So 0 plus j omega L. And j omega L, of course, J is 90 degrees. J omega L lies on the vertical axis, positive vertical axis. Okay, so these are the responses. Before we move on to the calculation of center frequency, cutoff frequencies, let's go ahead and do a problem. And actually, let me see. Actually, we need. Okay, so first we do the equations because we need the values of quality factor and all those to do the problem. So let's go ahead and solve that first. Okay. Now, what happens at resonance? At resonant frequency, like we discussed for the series bandpass filter, at resonant frequency, your capacitor and inductor, they're exchanging energy at all frequencies. But then all the energy that is in the inductor, it start exchanging with the capacitor at that frequency. So basically, they become independent of the source. So they don't receive any energy from the source. They just start exchanging energy among themselves, between themselves. And when that happens, basically, the source, if it's not sending any energy to the capacitor and inductor, the source assume that there is an open circuit over there. And the output becomes maximum output, which is the input value. So let's go back. At resonant frequency, capacitor and inductor starts exchanging full energy, let's say full energy between them and become independent of the source. So the Z equivalent or ZLC, I will write down the impedance of L and C. Basically, it tends to infinity at the resonant frequency. They become open. The source sees them as open circuit because source say that I'm not providing any energy to those components, so they are open for me. Because remember, anytime you provide energy to any component, that means you're supplying current to those components. If you're not providing energy to any component, that means you're not supplying current to that component. Energy component, that is, inductor or capacitor. So if source says, well, they are exchanging energy, whatever is stored in inductor is exchanging with a capacitor in half of the cycle, and then the capacitor in rest of the cycle sending the energy back to the inductor, right? Because it's a sinusoidal circuit, so you are going through cycles. At that specific frequency, let's say 1 kilohertz is your center frequency. So when you set your function generator at 1 kilohertz, and let's say you have the correct values of inductor capacitor, at that specific time, when you see the bandpass filter curve, you are on top of that curve, right? Your basically voltage is equal to input voltage. The output voltage equals to the input voltage. And that is only going to happen when those two components are not even there in the circuit and your terminals are open circuit. So you don't have any current. That means the output voltage and the input voltage becomes equal. There is no drop across the resistor, right? That means at that time, the combination of L and C, the equivalent combination of L and C is acting as an open circuit. Or since infinity is hard to analyze in math, we analyze using opposite of impedance. What is the opposite of impedance? What do we call it? Admittance. Admittance. Susceptance is reactance. Opposite of reactance is susceptance. So YLC tends to 0. The opposite of impedance tends to 0 and impedance tends to infinity. So this is admittance. Which is the opposite of impedance. All right, so let's calculate the impedance. So impedance, if two components are connected in parallel, the impedance, you add them together. And if two components are connected in series, impedance, basically you do the same way as you do parallel, not impedance, sorry, admittance. You do parallel impedance. So YLC at omega naught we're gonna calculate as the combination of YL plus YC. Why? Because remember ZLC, if they're connected in parallel, it is 1 divided by 1 over, I'll just write down ZL plus 1 over ZC. You're doing parallel combination, right?
Yeah, but he just means when we where you have ZL
Uh-huh.
equals.
Oh, ZLC, yeah, ZLC. We can go from Z and then calculate Y if you want. So let's go that route if you want. Let's do this first. Let's go from Z to Y. So your Z equivalent between L and C will be equal to 1 divided by 1 over XL plus 1 over XC, since they're connected in parallel. And that is going to give you 1 divided by 1 over J omega L plus J omega C. So when you calculate the admittance YLC, which is 1 over ZLC, that's going to be 1 divided by the whole thing. So you're going to get 1 over J omega L plus J omega C. This is easier to follow this. Anytime you have any question, make sure to ask. And remember, this is the same thing as I wrote earlier, YL plus YC, because YL is opposite of 1 over XL, or opposite of XL. So that's going to be 1 over XL, 1 over J omega L, and YC is opposite of XC. So XC is 1 over J omega C. So opposite or reciprocal of that is going to be J omega C. So admittance, if components are connected in parallel, admittance, you basically add the admittance of each component. And if they're connected in series, you're going to take the parallel combination of each admittance of the component. But anyways, let's move on. So at resonance, your YLC becomes 0. The admittance of the two components becomes 0. 1 over j omega L plus j omega C becomes 0. One over j omega L is equal to negative j omega C. And then we can do, we can just cross multiply. Yes. I'm sorry, omega naught. Okay. Omega naught. And we can just take the magnitude on both sides. So magnitude of 1 over j omega naught L, magnitude of negative j omega naught C. So 1 over omega naught L is equal to j naught, j omega naught. And which will give us omega naught square is equal to 1 over LC. And we will get our usual resonant frequency, which was also the resonant frequency equation for your bandpass filter, which is 1 over square root of LC. So equation is the same for both bandpass and bandstop for the resonant frequency. Yeah. What is the square root of 1? Okay, so, and of course, remember, if the frequency in hertz is given to you, then you just do 1 over 2 pi, 1 over square root of LC, 1 over 2 pi square root of LC. So that's hertz, that's radian per second, and that's hertz. Remember, is cycles per second. How many cycles are there per second? That's hertz. Let's do the cutoff frequencies. At cutoff frequencies, magnitude of h of j omega is what? Who's going to tell me? At cutoff frequency, magnitude of h j omega, let's say omega c to represent cutoff. What is the magnitude of the transfer function at cutoff frequency? 0.707 or 1 over square root of 2. You guys start flipping pages. I don't understand why you start flipping pages in your notebook or start looking here and there. Something that we discussed pretty much the last 3 classes. So we have the transfer function equation and we have the magnitude response equation right here. Omega L over r square 1 minus. So this magnitude response will be equated by 1 over square root of 2. So let's go ahead and do that. Omega L over square root of r square 1 minus omega square LC square. Okay. R square 1 minus omega square LC whole square plus, what is the next term? Anybody can tell me? Omega C represent cutoff frequency. What is the next term here? Omega L square? Omega L square. So omega C L square. Omega C represent cutoff frequency. So this is equal to half, 1 over square root of 2, not half, 1 over square root of 2. So we're going to go ahead and take a square on each side to remove the square root. WCL square over R square 1 minus omega c square LC square half. And we do the same thing like we did for the band, the series bandpass filter, cross multiplies, and then so we have I'm just going to write this down. So 2 times omega CL square, and then this is going to go on this side. This will be omega CL square. So when I take this on the left side, it's going to become a single omega CL square. So I'll skip one step. All right, let me just write down so that nobody will confuse. L square is equal to R square 1 minus. And that is going to give me okay. And now we take the square root on both sides, and we will write omega CL is equal to plus minus R1 minus omega CL. All right, let's go ahead and then we can write two equations here. So let's write omega CL plus R, and so if I use this minus and then bring this on this side, so that's going to be plus R minus omega C R L C. That's my equation number 1 is equal to 0. It should be omega square. I'm missing an omega square, which was here. That's omega square else. Omega square. So we write down this equation in terms of course, omega c. So I'm going to divide the whole equation by R, L, and C, and then write this down as omega c square minus omega CL divided by RL and C. So it's going to be 1 over RC. So 1 over RC omega C, and minus R divided by RL and C is going to be 1 over C. Two equations. And now we're going to go ahead and calculate the roots. So omega C, let's say 1 and 2, is equal to negative B, so 1 over RC plus minus square root of B square 1 over RC square minus 4AC, so plus 4 over LC divided by 2A, 2. And that will give me 1 over 2 RC plus minus 1 over 2 RC square plus 1 over LC. Okay, two roots. Which root is going to be the one that we are going to take? The positive one, right? The positive root, because frequency cannot be negative, remember. So we're going to take the positive root or positive value. And what will be the positive value? When you have the positive sign here. because if you take this negative sign, then this is going to become larger than this quantity, and your result is going to be a negative frequency. So you're going to take one root, which is 1 over 2 RC plus this, and that's going to be your upper cutoff frequency. Omega cutoff upper is 1 over 2 RC plus 1 over 2 RC square plus 1 over C. That's the upper cutoff frequency. Anybody can guess what will be the lower cutoff frequency, like we did the derivation for the last one, but instead of going through the derivation, anybody can guess what will be the lower cutoff frequency? Minus, so it's going to be a negative sign over here. This is not going to change. It's going to be a negative sign. So I'm just going to write down lower cutoff frequency. It's going to come from the second equation, which will have, right now, for this equation, we took the negative sign. And for the second equation, we're going to take the positive sign. So it's going to be omega CL is equal to R1 minus omega square CLC. And we're going to bring that on the left-hand side. It's going to become omega CL minus R and then plus omega C square RLC is equal to 0. So from that equation, you're going to get the lower cutoff frequency, which will be, I'm not going into the derivation. Lower cutoff frequency. It's going to be negative 1 over 2 RC plus 1 over 2 RC square plus 1. That's going to be a lower frequency because from the square root, you're subtracting 1 over 2 RC instead of adding 1 over 2 RC. So that's going to be a lower value. So cutoff frequency in general, omega cutoff upper and lower. We also call them omega 2, 1. Upper is usually 2 and lower is usually 1. They are given by 1 over 2 RC square plus 1 over LC plus minus 1 over 2 RC. So these are both frequencies, upper cutoff and lower cutoff. If you relate that to the time domain that we learned, 1 over 2 RC was what in our transient? Alpha, your Napier frequency, right? And 1 over LC was omega naught. So if you relate 1 over square root of LC was omega naught, which it still is. So that's square root of alpha square plus omega naught square plus minus alpha. Same goes for the series, because in series we have R over 2L, which is alpha for series, the Napier frequency. Let's calculate the quality factor. So bandwidth, of course, bandwidth is omega upper, cutoff upper minus omega cutoff lower. So when you subtract that, this term is going to be cancelled out, and we will only have 1 over 2 RC. Quality factor. Again, quality factor definition is the same, 2 pi maximum energy stored in the circuit divided by energy lost per period. Per cycle. That's how you calculate the quality factor. And as we discussed on Monday, maximum energy is stored. Energy, of course, is stored in inductor and capacitor. Yes. Is it? Oh yeah, 2 times 1 over 2 RC. So 2 is going to be cancelled out. That's correct. So that's going to be simply 1 over RC. Because you're adding them together, so it's going to be 2 times 1 over 2 RC. So 1 over RC. Maximum energy stored, energy lost per cycle. So maximum energy stored is at resonant frequency because the energy that is stored in the capacitor is maximum, which is being exchanged with the inductor. So that occurs at the resonant frequency. So Q is going to be reflected by that fact that it is Q naught. That is at resonant frequency, you have the maximum energy stored. And after derivation and stuff, basically you have R over XL naught as the final expression for your resonant frequency for parallel RLC circuit, which is given by R over omega naught. And also, so yes. Yeah, I'm putting that basically. The next item is that since the reactants, they become equal to each other, so R over XC naught, which will be R over 1 divided by omega naught C. So you can also write that down as omega naught RC. The quality factor can be given by this. For the series, it was opposite, XL naught over R or XC naught over R. That was for the series. And for the parallel is the opposite. Now, again, cutoff frequencies in terms of omega naught and Q and B. We can also look at that. And since our cutoff frequencies are cutoff upper, cutoff lower is equal to square root of 1 over 2 RC square plus 1 over LC plus minus 1 over 2 RC. So we have Q is equal to, Q naught is equal to omega naught RC which means RC is equal to Q naught over omega naught or 1 RC equals omega naught So we can write this down as what is it? Omega naught over Q, 1 over RC. So omega naught over Q naught 2 times square plus omega naught square plus minus omega naught over Q. And since bandwidth, actually 1 over RC is the bandwidth, right? 1 over RC is the bandwidth. So omega naught over Q naught is equal to bandwidth. We can also write down in terms of bandwidth. One over, or bandwidth over 2, bandwidth over 2 square plus omega naught square plus minus bandwidth over 2. So these are just different variations of cutoff frequencies. Where bandwidth is equal to 1 over RC, which is equal to omega naught over Q. Naught over Q. And omega naught can also be calculated, center frequency. Also, square root of omega upper cutoff times omega lower cutoff. For large Q values, omega upper cutoff is approximated as omega naught plus half of the bandwidth, and omega lower cutoff is approximated as center frequency minus half. And this is generally true if Q is 5 or more than 5, then the approximation is pretty close. If Q is small, then exact cutoff frequencies and approximate will have difference, as we again saw that on Monday when we were solving problems. Okay, guys, let's go ahead and take a break. I have one problem, so we're gonna do this problem after the break, and then I'll give you the quiz. So let's go ahead and take a break and then finish that problem before the quiz. So we are going to do one problem based on the parallel RLC circuits. And in this problem, we are going to design a parallel RLC filter and then plot the magnitude response and phase response. Design a parallel RLC filter with capacitor value to be 10 nanofarad, center frequency to be 10 kilohertz, and bandwidth to be 1 kilohertz. Remember, anytime we are designing a circuit, that means we are calculating the values of the components that are not given to us based on the other information. So in this case, capacitor value is given to us, and the other information is that this is the center frequency we need, this is the bandwidth that we need. So even if it is not given to you that what you're calculating, remember in this case, you're calculating the value of R and you're calculating the value of L, the two component values to design this filter. Calculate R, L, quality factor, and upper cutoff frequency, and the lower cutoff frequency. So we design it, we calculate the value of RL, and then from the circuit design, we will calculate quality factor of the circuit, upper cutoff frequency and lower cutoff frequency. Okay, so F naught and B, two quantities are given to us. We know that F naught is, or omega naught is 1 over square root of LC. Since omega naught is 1 over square root of LC, F naught is 1 over 2 pi square root of LC. From that, we can calculate the value of L because C is given to us. And I'm just going to write down, I have the calculation here. L is going to come out to be 25.3 millihenry. Okay. Next value we can calculate from the bandwidth. Also, we calculated the bandwidth equation to be 1 over RC, and from that R will be equal to 1 over bandwidth times C. Now remember, this bandwidth we calculated was in radian per second because we subtracted omega 1 minus omega 2 or omega 2 minus omega 1. So make sure you convert this bandwidth into hertz because hertz is given to us, not radian per second. 1 kilohertz is given to us. So when you're calculating this, two pi b, whatever. 2 pi times, what is the bandwidth? 1 kilohertz, right? 2 pi times 1000 times C. Calculate myself. And it's coming out with 15.9 kilo ohms. That's the font size. $15.9 kilo ohms. So we designed the filter successfully. We found the value of L and we found the value of R. Now we're going to find the cutoff frequencies and all those things. So remember all the derivations that we did here, they were in radian per second. So anytime hertz is given to you, you have to convert it appropriately from hertz to radian per second. So the cutoff frequencies, yes. Capacitor is 10 nanofarad, yeah. Quality factor is, what is that, the center frequency over bandwidth? Yes. Chris, you have a question? Bandwidth is 1 kilohertz, right? What I gave you? 1 kilohertz? Why did you say 800 hertz? You said 800 hertz? Yeah. We did not convert into hertz, we converted into radian per second. 2 pi times 1000. Oh, okay. Yeah, convert into radian per second. Yeah, not hertz, sorry. It's given in hertz. Convert into radian per second. Radian per second. Inductor is right here in front of you, 25.3 millihenry. So quality factor in this case, Q is equal to, again, you can do omega naught over B, or you can do F naught over B, because omega naught is 2 pi F naught, and B, if it is given in radian per second, then you can convert that, and or if given in hertz, you can convert into 2 pi times B. So 2 pi in the numerator and denominator will cancel each other. So this is in radian per second, and then you can put simply B in hertz. So both are valid equations, because 2 pi in the numerator and denominator is going to cancel each other. F naught over B, 10 kilohertz over, okay. Yeah. So this is a large enough value of Q naught, approximate and exact value of cutoff frequencies should be very close to each other. We can calculate both. First approximate. Upper cutoff frequency will be center frequency plus half of the bandwidth in hertz. Center frequency is 10 kilohertz. Half of the bandwidth is going to be 500 hertz. That's going to be 10.5 kilohertz. Approximate, this is the approximate. And the lower is going to be 9.5 kilohertz. And now we can calculate the exact using the equations. Remember, bandwidth difference is going to be 1 kilohertz between the two. Divided by 2 pi. Times. strange value. Let's see. A is 1/2 RC, and then F naught. Oh, whether not is incorrect. Okay, that's why. Square. So this is coming out with 10.518. You know, 10.5. FC lower is 9.518 crore. So it's not very far away from what we calculated earlier. Approximates are 10.5, and exact is 10.518. So 18 hertz deviation, right? Yeah, 18 hertz deviation between the two frequencies. The cutoff exact and cutoff approximate. So 18 hertz is not that much. And finally, we're going to plot the response real quick. Let's go to the that's my h of j omega. So let's go ahead and use this. Omega is equal to 10, 10, x minus 6. All right, so h is I times omega times L divided by R times 1 minus omega square times L times C plus I times omega times L. Plot the response curve. I'm plotting it as well. This is the response curve for both. As you can see clearly, it's a, of course, band pass filter. Top is the magnitude, bottom is the base. Same code that we used last on Monday. Same code, except what is changed? Transfer function is changed. That's it, right? That's a different transfer function that I used today, but the approach is exactly the same. Transfer function, of course, we have is this transfer function, right? RLNC. So C is 10 nanofarad given to us, and R came out to be 15.915 kilohertz, and L came out to be 25.3 millihenry. Millihenry. L millihenry, 25.3 millihenry. Exact was, let's see, exact is 10.518 kilohertz upper and 9.518 kilohertz lower. Approximate is 10.5 kilohertz upper and 9.5. Exact is 10.518. So 18 hertz deviation, basically. That's not a lot. That's perfectly fine. For this, of course, to plot the curve, you only need the values of L, R, and C. That's all you need. And of course, you are going to define your omega. I'm defining my omega starting around 10. Well, I converted omega into a frequency hertz. So I'm starting at 10 hertz, going up to about 1 megahertz, step size about 10 hertz.